Hello and welcome to a new video on cryptography for everybody. Today we have a different kind of video, and actually it's not about cryptology at all. Today I want to give you an introduction to memory forensics. A few months ago I gave a test lecture about memory forensics, and now I translated it from German to English, and in this video I want to give you that introduction too. The video is structured into 3 different parts. In the first part, I will give you an introduction to digital forensics, that is a theoretical part. I will give you a few definitions. I will show you the subfields, and then we will have a look at the basics of memory forensics. After that, in the second part of the video, we will have a look at Windows memory forensics, and this is a practical part. I will show you a scenario that I invented, and then we will go through the different phases of the memory forensics analysis, namely the identification phase, the data backup phase, the data analysis and documentation phase, and the presentation phase. And finally, I will give you a summary and a conclusion. First of all, I want to give you a general introduction to digital forensics. What does the term forensics mean? The term originates from the Latin forum, which means marketplace. In ancient Rome, court proceedings, investigations, pronouncements of judgment, and the execution of punishments were conducted publicly in the forum. Today, forensics encompasses those fields of work where criminal actions are systematically identified, analyzed, or reconstructed. I took this definition from the Gabler Wirtschaftslexikon, which is translated to Gabler Economic Dictionary and translated it to English. Let's have a look at a definition for digital forensics by the German BSI. Digital forensics is a rigorously methodical data analysis on data carriers and in computer networks to clarify incidents, taking into account the possibilities of strategic preparation, especially from the perspective of the system operator of an IT system. This definition comes from the BSI Leitfaden IT Forensic, translated to BSI Guide IT Forensics in the version 101 from March 2011, and I also translated it to English. We can get a few important general keywords from these 2 definitions. First of all, forensics is always systematic. You investigate criminal actions, you do a rigorously methodical analysis, you do it in a strategic way, so you do some preparation, and finally you want to clarify what happened. Then we have a few important IT keywords that we can get out of the digital forensics definition from the BSI. We have data analysis, so we work with data from data carrier or computer networks, and we have incidents that we want to analyze. Now let's have a look at the subfields of digital forensics. And I divided these subfields into main subfields. We have the data carrier and data storage forensics, and we have the computer network forensics. In the data carrier forensics, we have the volatile random access memory that we analyze. We have floppy disks, CDs, DVDs, Blu-rays, USB drives, memory cards, or mobile device storage. And we have hard drives that can be magnetic or SSDs. The memory analysis is an analysis of data in use, and the storage analysis is analysis of data at rest. Then we have the computer network forensics. Here we analyze how PCs communicate, routers, IoT devices, intrusion detection systems, servers, firewalls, mobile devices. In general, devices that communicate digitally. And we also call this the analysis of data in transit. In this video, we will only have a brief introductory view or look at random access memory and how we can analyze these. Let's have a look at the general procedure of forensics or memory forensics. And the main rule that we always have to follow is we change nothing as far, of course, as it's possible. Because we want to secure evidence and we do not want to destroy, alter, or even create evidence. And we always work, if possible, only with copies of the data. Here we have 5 phases of forensics or memory forensics, and this scheme is based on this Security Insider DE webpage that gave a really nice introduction into that topic. This is in German, so for the German viewers this may be interesting. The first phase is the identification phase. Here we create an inventory of the incident to be investigated. We do an initial presentation of the initial situation, and we create a description of the questions to be clarified. In the second phase, we do a backup. That means all data is backed up. In our case, a copy of the memory. And we determine whether the IT system can continue to operate despite the incident. It could be that an attack on an IT system is still going on, and if we keep the system up, it would be damaged even more. Then we have the analysis phase. Here we do the actual investigation of the system regarding the incident. And we do identification of processes, causes, responsible parties. And in parallel to the analysis, we always do documentation. All steps carried out in the analysis are recorded and documented. So analysis and documentation phase are performed in parallel. Finally, we give a presentation, for instance, to the customer for whom we analyze the system. Here, the collected data and documentation are summarized in a report for the customer. It contains facts like perpetrator's identity, if possible, extent and duration of the act, causes, and maybe, if possible, motives. Here are now some examples of digital traces that we can find in random access memory in RAM. We can, for instance, find running applications. These are the processes and threads executed by the computer. Then we can find the browser history in memory. We could find clipboard contents, so things that someone copied and is still in the clipboard of the computer. We can see open and closed network connections of the system. We have cached files in memory. We can have chat messages of chat applications in the memory. Then, and this is important if we want to have a look at other sources despite the memory of the computer, we can have account login information. So we could, for instance, then log in into a cloud system. And also, and especially for this channel, very interesting, we could have cryptographic keys, for instance, to decrypt encrypted material. Now let's discuss what is actually RAM. And as I already said, RAM stands for Random Access Memory. And that is memory that the computer can access at will. That means each memory cell can be individually addressed, read, and written to. And technically, there is static RAM, SRAM, and dynamic RAM, DRAM. The difference between these two types of RAM is that the static RAM doesn't need a refresh signal. Dynamic RAM needs a continuous refresh signal, for instance, produced by a clock, and if you stop refreshing dynamic RAM, it loses its content. Usually, RAM is managed and protected, of course, by the operating system and specific security mechanisms of a CPU. The keyword here is a protected mode of modern CPUs. Only the operating system can truly do everything, so read and write in every position of the RAM, or it must allow us to do so. Keywords here are the user mode and the kernel mode. User mode processes don't have these privileges as the kernel mode processes, so user mode processes are not allowed to read and write everywhere in RAM, but kernel mode processes, like the kernel itself or drivers, are allowed more or less to do anything in the RAM. And one big problem of RAM is, as soon as the computer is turned off, all data stored in RAM is more or less gone. Sometimes it resides a few seconds, maybe a minute or so, but then it's completely gone. And this process happens very fast. On the right side, I have an example for DRAM memory modules here. Now let's answer the question, how is RAM logically structured? And modern operating systems, for instance Windows and Linux systems, use so-called paging for virtual memory management. What is virtual memory? Virtual memory means that we have independent address space provided for a single process. So each process has its own memory space. It starts at address 0 and continues to the largest possible address. And virtual memory is divided into so-called pages. For x86 and x64 systems, we have 4 kilobyte pages and we have large pages of 4 megabytes. The physical memory is then divided into frames accordingly. And the mapping between pages and frames are managed using so-called page tables. And finally, pages can be swapped out to the hard drive to create space in memory. Let's have a look at an example to understand what all this means. We have here the virtual memory of a single process. We have different pages here, and these pages are mapped by page tables. You can see these arrows here to the physical memory. This is done by the operating system. And the funny thing here is that even memory that in our virtual memory comes after each other, so we have the green block after the blue block, in the physical memory it can look totally different. And you can have, like this block here, memory or virtual memory that is not even part of the actual physical memory right now, because it's swapped to the hard drive. That means that it's written to the hard drive and removed from the physical memory. If the process now wants to access this part of his memory, it will cause the operating system to load the memory from the hard drive through an interrupt. Then the memory is written into some part here in the physical memory. There's a new assignment, and then the process continues and it can read and write its own virtual memory. And each process of the operating system, or each process running on your computer, uses this virtual memory. It has its own virtual memory. Now let's have a look, how can RAM be read out or backupped? Because before we analyze anything, the content of the RAM must be secured. And there are basically two types that are called local attack possibilities. Because it's actually as if you attack the hardware or the RAM. We have hardware-based attacks and software-based attacks. The main difference is that with hardware-based attacks, no root access is needed. So you don't need to be root on the system. So the biggest or the administrator with the most privilege. And we have then software-based attacks where root access is needed. Examples for hardware-based attacks is the cold boot attack, for instance. There are two types. You could just switch off the computer while it's running, then instantly switch it on or do a reset, and then put, for instance, a USB stick into the system, boot the system, and try to read out the complete content of the memory. Clearly, booting a USB stick also starts or also overrides the memory, so with this attack it's very difficult. Another way of a cold boot, an actual cold boot attack is, or a cold attack is, that you use like some ice spray. You spray the memory hardware in your system, then you switch it off, you cool it down to very low temperature, you remove the RAM modules, you put it in a special device, and then you use the device for reading it out. And the idea of cooling down the memory is that the memory cells keep the data that's in them longer. It could be that when you cool down a memory, that the memory remains, or the data in the memory remains for several hours. Then the second part of hardware-based attacks is the so-called DMA attack. That means direct memory access. For that, you could, for instance, use FireWire, USB 4.0, or PCI, because these operate besides this actual CPU. You put in a device, and the device gets direct access to the memory, and you can just read out the memory. Then we have software-based attacks, as I already said. Here, we could just use, for instance, if we have virtual machine snapshots, these contain the complete memory. We could use hibernation files. A hibernation file is created when you let your operating system or your computer sleep. Then the operating system writes the complete memory to the hibernation file. Then we have page files and swap files. Remember, parts of the memory are written to the hard drive, and these are written to these files. But of course, we can use, or these offer only limited use, because not the complete memory content is written to these files. Then, in the case our system that we want to analyze crashed, modern operating systems also write crash dumps that can contain the complete memory. And finally, we could use tools if we have root access. And in this video, for instance, I use the Belkasoft's live RAM capture for 32-bit and 64-bit Windows. This is a tool that allows, when you have administrative access, to read out the complete memory of a system and then, for instance, copy it to the USB stick. Now we have a copy of the complete RAM. What do we do now? Now the actual forensics analysis takes place with the help of tools. And I will show you especially one tool that we will use here in the video. That tool is called Volatily 3. It's a Python-based memory forensics framework and it requires Python 3.6. It's open source and free, so you can download it if you want and use it. It's a very established tool and you find plenty of online documentation on the internet. Here's the website of the Volatily Foundation, the developers of Volatily, and you can find Volatily source code on GitHub here on this URL. Volatily provides a variety of analysis capabilities. It offers a variety of profiles. A profile means that Volatily understands the operating system or the memory of the operating system that you are currently analyzing. Each operating system has more or less a fingerprint or a way how it organizes its memory. And Volatily, by using a profile, is able to read out, using this profile, the structure of the memory and understand it. Then finally, Volatily 3 is a command line based tool. As an environment for the analysis, we use Kali Linux that you can find on kali.org. It's a penetration testing distribution. It's also open source and it's based on Debian Linux. But due to licensing reasons, Volatily is no longer included in Kali Linux. So you need to download it manually, and you just do it by just cloning the GitHub repository. Then you can call the Python scripts of Volatily. Now we come to the practical part of this video. We start the practical part with a scenario. We are right now employees of the IT security and IT forensics company V Forensic Analysis GmbH from Pullach. Our company specializes in digital forensics, particularly in the field of so-called critical infrastructures, for instance, like power plants. And our task is that the medium-sized energy producer Nuclear Power AG from Kalka has reported a presumed IT security incident to the German Federal Office for Information Security, the BSI. And it has to report these incidents to the BSI according to the Federal Office for Information Security Act, the BSI-Gesetz, because it has a reporting obligation. The internal emergency response team of the Nuclear Power AG is baffled. They don't know what happened, they don't know what's currently going on, they only know that something bad happened. The production computers that are not networked, that means they are air-gapped, they are not connected to the internet, seem to be causing issues. And we are now tasked with conducting IT forensic analysis on the production computers. Keep in mind that I made up this complete scenario here. It has more or less no relation to the reality. Of course, it's inspired by some real actions, but this here is made up by myself, just for the purpose of this lecture and this video. The first step that we follow when analyzing these computers is the identification phase here. So we perform and create a concrete inventory of the incident under investigation. And gas centrifuges used by the Nuclear Power AG for uranium enrichment experience above average rates of failure. So you have here these uranium centrifuges that the company uses to enrich uranium, and a few or more, many of these start to fail, and the number of failures is much or way above the average rates of failure. The Nuclear Power AG utilizes Siemens SIMATIC S7 programmable logic controllers, PLCs, for the control and monitoring of the centrifuges. You can see this unit here. This is a Siemens SIMATIC S7 unit, and these units control the Nuclear Power AG's centrifuges. To program the Siemens SIMATIC, technicians still use outdated Windows XP laptops, as you can see here. And it appears that these laptops are uploading faulty programs onto the Siemens SIMATIC S7. As a failure of additional centrifuges is feared, the uranium enrichment process is being halted. You will likely say now that using Windows XP laptops is a really bad idea and very outdated. But keep in mind that many industrial facilities, because of incompatibilities, of lack of money for updates, or even just because the machines are not able to work with newer software and hardware, still use outdated software and hardware. And so having a Windows XP PC in an industrial environment or even older PCs is nothing you should wonder about. Now we come to the second phase, the so-called data backup phase. Now we back up the data of the laptops. In addition to the RAM, of course, the hard drive and possibly other storage devices would of course be backed up too, but this is part of another video. But we will have a small glimpse at also hard drive analysis later. The laptops are powered off, but of course we have administrative access because we got it from the employees of the power plant. We use Belkasoft Live RAM Capturer to secure the live memory to USB stick after the boot process of each laptop. And clearly we use a separate USB, an individual USB stick for each of the computers. Why do we do so? Imagine one of the computers has malware. The first, for instance, you put in the USB stick and then the malware is automatically copied onto the USB stick. Then you copy the memory, you go to the second computer, and then you take the malware from one PC to another. So we cross-contaminate all the computers. Because of that, you use a single USB stick for each computer. And of course, these USB sticks were previously completely wiped, they are completely empty. Now we have a live backup of a Windows memory. We are now on a virtual machine here. I just want to demonstrate you how the RAM capture works. You have to give it administrative rights. When the Belkasoft Live RAM Capturer pops up, we just press the capture button here. Since we have administrative root rights, we can just copy the memory now. It downloads the memory, and you can see as we have here 2 GB of memory in the machine. And we now have this mem file here that we can use for further analysis. Now we have a copy of the memory of a machine. What do we do during the memory analysis now? The secured memory is transferred to the Kali Linux analysis machine and analyzed using Volatily. And a note, of course, as I already said, the hard drive will also be examined in more detail, but this could be part of another video. And we analyze the machine for the presence of malware. We want to identify the running processes on the machine at the time of the memory snapshot. We want to extract suspicious processes from the memory snapshot. And we want to perform analysis of the extracted processes for malware using VirusTotal. This is a web page where you can upload, for instance, fingerprints of processes or executables, and then VirusTotal has a lot of antivirus programs checking these and giving you a report. Now let's analyze the memory that we captured using Volatily. And of course we want to extract the process list. I have here now a copy of a Windows XP machine. This is a memory. This is not the memory I captured in the example before. This is a memory dump that I downloaded from the internet for this video here, or for the lecture. Now we go to the desktop, to Volatily 3. No, we are wrong here. We want to go to the folder where the Windows XP machine RAM capture is. And now we can use Python and then call the volatility framework. This is always called with vol.py. And then you can give it arguments. For instance, you can give it a file. The file is the captured memory. In our case, a Windows XP machine capture. And then we want to see the Windows information. This takes some time because it scans through the file. Here we have the result. And here you can see, for instance, the timestamp of the capture, the major and minor versions of Windows, and so on. And what I do always when I analyze such a machine, I always pipe the result that Volatility gives me to a file, because we can use this file later for our reporting. We have the file here now, we can open it, and here you can see the same content that we saw in the console, and this can be later used for the analysis reporting. Now we want to extract a list of processes running in our system, or our Windows XP system. To do so, we use the windows.pslist command. This analyzes our memory dump and searches for all the processes running. And here you can see a list of the processes. And as before, I also pipe the list of processes, the result of that call of Volatility, to a text file that we can later use for our reporting. Here you can see the text file that was created. And here we have a list of all running processes at the time we made the memory dump. It's as if we have frozen the system in time. There's a second possibility to analyze processes, and this is PS tree. That means process tree, or processes tree. It's basically the same as PS list, but it gives us a tree, because processes have some kind of relation to each other. So you have father and child processes, or parent and child processes. I also pipe these into a text file. And here you can see now which are parents and which are child processes, because the child processes are aligned a little more to the right. Now that we extracted a process list of the Windows XP machine, let's have a look at the process overview of Windows XP and have a simplified view here. We have different exe files, different processes running in the background when you start a healthy system. We have the session manager subsystem SMSS exe, we have the client server runtime subsystem CSRSS.exe, and so on. I won't go over these processes here all in detail, but if you analyze a Windows system, you should have a look at which processes should be there and which should be not there. Here you have also a tree, which processes should run on a Windows XP machine. As I said, this is a simplified version of Windows XP Professional 64-bit, since the machine we analyze is a Windows XP machine. And you can, for instance, see that the system starts one SMSS.exe, the SMSS.exe started one winlog on exe, we have one explorer with no parent, and so on. Good to know here is now how many instances of a process should there be, what parent-child relationship should exist between the processes, and the path to the executable file, the user account, and many more informations we can get about a healthy Windows system. Now let's review our original individual processes. I created here a nice table of all processes running in the machine we analyze. We have the process ID, that is the ID, so the number of the process. When a process is started, it gets from the operating system a number. And every time a new process is started, this number is increased or incremented. So we have no two processes with the same process ID. And we also know which is the parent process. So the system here, the system process, the main process you could say, or the kernel process has a process ID 4. It has no parent ID, or it has a 0. Then we have this SMSS.exe here. It has the process ID 376, and it was started by the system. And using that, you can reconstruct the complete tree of which process started or spawned which other process. Now we have a question here. Which of the processes here are suspicious? And I suggest that you stop this video at this point and have a look at detail at this table here, and maybe you can already spot processes that are suspicious. You could also go back one slide and see the overview of which processes and which number of processes should be there. So just pause the video and then continue the video, and I will give you the result, which processes are suspicious. And the answer is, We have two suspicious processes here at a first glimpse. We have two additional lss.exe. We know that there should be only one lss.exe and that it should be started by the 624 here, and this is a winlogon. So winlogon starts lss.exe. But we have two additional ones, the process with the ID 868 and the process with the ID 1928, these two here. And these were also not started by the winlogon, they were started by 668, and 668 is services.exe. So these two processes are currently running as services. Both have winlogon, as I said, not as parent, and we'll proceed now to extract and check these two processes or the data of the processes for further analysis. Let's extract the suspicious processes. Here we once again in the console of the Kali Linux, and we want to extract the processes. For that, we use again the pslist command, but now we provide a process ID. And one of our processes we want to analyze is the process 868 with the process ID 868. And then we use a dump command to dump the memory of that process. Now we have here the dump file, and we can use the dump file for further analysis. For the further analysis, I use the SHA-SUM tool of Linux with SHA-256 to compute a SHA-SUM of the process data. We have here now an overview of all hashed process dumps. And our task is now to determine which of the process dumps contains malware. And we check these processes using VirusTotal. To do so, we go into the browser. I copied the hash value into the clipboard, and then I go to search and paste the hash value. And then we get a report here that tells us which different antivirus systems found something or knew this hash value here. I did this analysis for all the files. Let's have a look at the result. And the result of the VirusTotal analysis is I analyzed all processes, and all processes are infected with malware, or at least one analysis tool flags each of the processes. And our two suspicious processes here especially were flagged many times by different antivirus softwares. We have 58 of 72 VirusTotal analysis here flagging this lss.exe file, and here we have 49 of 66 of these lss.exe files. But can this really be true? Are all processes and all files behind the processes on the hard drive infected by malware? Now we have a glimpse at hard drive forensics, and we want to perform verification of digital signatures of the associated executable files of the processes. And as I said, this is a small preview of disk forensics. Maybe you know of one of my previous videos that almost all Windows executables, so .exe files and libraries, so DLL files that are part of Windows, have been digitally signed by Microsoft. A digital signature is some kind of digital fingerprint. And if malware has infected the associated .exe files, the digital signatures and PE checksums, this is part of the .exe file, also become invalid. So what is a digital signature? Digital signature means that we have a software signing certificate here. Microsoft has, of course, many of these for their products. And they use a signature creation tool to, for instance, sign the Explorer.exe. So they compile the Explorer, they use the binary code, the Explorer.exe file, put it into the signature creation tool together with a software signing certificate. Of course, they have the private key for that certificate. And then they digitally sign the Explorer.exe and add a signature to the exe. Your operating system, when it starts the Explorer.exe or any other file, it can check for the validity of these signatures, and if a file is not valid or the signature is not valid, it can not execute it or even start it. Here, the data of processes in memory and also executable on the hard drives are altered, of course, by malware. But malware creators do not possess Microsoft certificates. Clearly, Microsoft keeps them very secure. So signatures cannot be repaired without a valid certificate, so we can identify changed files, changed by malware for instance, by checking the validity of the certificates. And here is a verification example of the digital signatures of executable files. And as an example of a valid digital signature, I used our cryptwin.exe. This is the main file of cryptool2. And this here is the output of the OSSL sign code verify tool with cryptwin.exe. You can see here the current PE checksum and the calculated PE checksum. These have to match. That means the file has not been altered. We see here's the timestamp when we used our software signing certificate to sign that file. And the tool also says number of verified signatures 1 succeeded. So cryptool2 or the cryptwin.exe here has not been altered. So there's no malware in cryptwin.exe. Now back to our two Elsass.exe files. So I analyzed these Elsass.exe files using VirusTotal. Remember PID 868, and it said that we have 49 of 66 tools flagged this file here as malicious. So what do we have here? The Microsoft Defender tells us this is Trojan win32duq.e, and Dr. Web tells us even this is Trojan Stuxnet.8. What is Stuxnet? Stuxnet is a network worm from the year 2007. It was discovered in 2010 and it was active until 2011. Stuxnet is a professional sabotage software for cyber attacks against Iranian nuclear facilities. So it did what we have seen in our company that we analyze. It attacks the uranium centrifuges. Here are a few facts. Stuxnet spreads via USB storage devices and local networks. It seeks out Cymatic S7 controllers to manipulate them. And the variant found here, called duq, is a successor to Stuxnet. And the authors of duq likely had access to the source code of Stuxnet. You may wonder who is the author of Stuxnet. Actually, we don't know exactly who was the author. There are rumors that this could have been large secret services, for instance from the United States or from Israel. And Stuxnet utilized 4 zero-day exploits to fulfill its purpose. A zero-day exploit is an exploit that has not been publicly discovered yet, so this was is a very sophisticated cyber weapon, Stuxnet. Now in the final phase, the collected data is compiled into a report. And here are the contents and structure of the report. The report should be understandable for individuals who are no technicians. You should give a summary of the steps performed, for instance, a single page. After that, it follows the entire story of the investigation. What was done? We did a memory analysis, we identified processes and dumped them, we used the process dumps and examined them for malware. Why was it done? We wanted to identify malware. Then we could produce figures to illustrate connections between, for instance, processes or what we did so far and why we did it. You should also include all the data collected during the process. That's why I created all these text files. And you should mention all the file, process names, hash values, timestamps, process IDs, parent process IDs, etc. And finally, of course, we could draw conclusions. Our conclusion was that the turbines or the centrifuges were attacked by a worm called Stuxnet that manipulated the Cymatic S7. And then, of course, we should potentially suggest next steps. Suggested steps would here be to reinstall all the laptops in a clean environment, reinstall the Cymatic S7 with cleaned laptops to clean all the systems from the malware. And a good general overview of forensics reporting you can find on this web page here. This gives you a good introduction to forensics reporting. Now let's come to the summary and conclusion of this lecture. And here I've selected key questions, the lessons you should have learned. You should have learned what is forensics and digital forensics. You can find the answers on slide 5. What can we find in the memory of Windows PCs? We also answered that. You can find that on slide 8. For instance, processes, clipboard content, chat, etc. We used it to find processes. How can we read the memory of PCs? Slide 11. Two different ways, software and hardware. We use the software tool Belkasoft RAM Capturer. How can we display and dump extract processes? We used Volatility for that. Have a look at slide 19 and onwards. What can we use hash values of processes or files for? We can use it to determine if malware is inside these processes. Slide 77 and onwards. Then, what is a digital signature of an executable? We saw that, for instance, Microsoft signs the executables, that an operating system can check if a file has been altered. Also, you can use, or we can use these signatures to see that. Slide 27 and onwards. What can we use these digital signatures for? I already answered that. We can see if a file was altered or is in its original state. Now, this is the end of the video. If you are interested in more details, I highly suggest that you have a look at these documents and links here. Clearly, in this video, I only gave a very, very brief introduction into memory forensics. There's much more you can do and have to do when you analyze the memory of a computer. And especially the Windows internals books are very interesting when you analyze, for instance, Windows machines. Here you have more general introduction for memory forensics. The BSI Leitfaden IT Forensic is interesting for the German viewers of this channel. And then you have the Interpol guidelines for digital forensics, first responders, best practices for search and seizure 2021. This is also interesting. Yes, and this is everything I wanted to show you in this video, in this lecture. I hope you liked it. If yes, please give a thumbs up. This really helps me to grow the channel and make it more popular. The more thumbs up you give, the higher the chance that I continue to produce also videos on digital forensics. I think it's a very interesting topic. It is not really related to cryptography, mostly, but of course with digital forensics, cryptography is also a part. So it's not the main part, but for instance, extracting keys, analyzing ciphers, and so is also done in digital forensics. Yeah, and as I said, this is everything I wanted to show in this video. So thank you very much for watching and see you in the next video.